Welcome everyone to today's webinar jointly hosted by CASA and CWEA on food waste co-digestion in California. This is a summary and a recap of a long anticipated report recently released on August 24th by the California State Water Boards. They had commissioned an analysis of co-digestion excess capacity at our wastewater treatment plants in California, and Carollo Engineers executed that work, and the report, as I say, was just released, and we're here to summarize it and answer questions on it. And welcome everyone. I'm Greg Kester, Director of Renewable Resource Programs for CASA, the California Association of Sanitation Agencies. And we look really forward to a great presentation today. This is just a disclaimer put up by CWEA, so everyone is aware of it. And just some ground rules for the webinar today. Please use the chat function at the bottom of the screen for administrative or technical questions that can be addressed to CWEA, or if you want to talk amongst your colleagues. And use the Q&A function to the right of that to ask questions of the presenters. We'll have a whole Q&A session after all the presentations have completed. And we will not use the raise hand function today. Fortunately, this has been a very popular webinar, so there are too many attendees for us really to use that effectively. With that, I'd like to introduce our speakers. And I should mention that Charlotte Ely from the State Water Boards, who really was the driving force behind allowing this report to be completed and commissioned, has some technical difficulties, but we hope that she will be able to join us as we go on here. So our first speaker is Rashi Gupta. She is a Vice President and Project Manager with Carollo Engineers. Rashi is specialized in delivering sustainable solutions for biosolids management and wastewater treatment. Throughout her 17-year career. And she obtained her Bachelor's of Science in Civil Engineering from UC Davis, her Master's from the University of Texas at Austin. Rashi now serves as Carollo's Biosolids Technology Integration Lead, focusing on solids projects throughout the country. She's a licensed civil engineer in California and a member of the WRRF Residuals and Biosolids Committee, serving as the Vice Chair of the Solid Separation Subcommittee. And our next speaker will be Elizabeth Charbonnet. She is a lead environmental engineer at Carollo. She joined Carollo in 2013, and since that time, focused on wastewater solids management. Her experience includes integrated master planning, innovative biosolids treatment technologies, cogeneration design, and grant applications. She holds a master's degree in environmental engineering from UC Berkeley, Bachelor of Science degree in Environmental Engineering from MIT. And lastly, we have Sarah Delorier, who is a Vice President with Carollo. And Sarah has been specializing in sustainability, resource recovery, climate change analysis, greenhouse gas emission management, biosolids management, and master planning throughout her 17-year career. She's a Vice President and Project Manager at Carollo, serving as their climate change and resilience lead. And she also serves as the program manager for CASA's climate change program and the Bay Area Biosolids Coalition. In addition, Sarah is the chair of the Bioenergy Technology Subcommittee for the WRRF Residuals and Biosolids Committee. Sarah received both her bachelor's and master's degrees from the University of Michigan. With that, I'd like to turn it over to Rashi to begin for us. Thank you.
Thank you, Greg. So Charlotte is trying to get on, and I think once she is on, we'll kind of pause and let her provide the State Water Board's input. She might not be having a little bit of difficulty this morning trying to get on, but thank you very much for joining us this morning. We're very excited that the report has been finalized and issued. And today's seminar title, or the webinar title, is Food Waste Co-Digestion in California, the role of, first typo, water resource recovery facilities and investment needs to maximize co-digestion in support of SB 1383. First of all, I'd like to thank our project team. Sorry. Okay. I'd like to thank our project team, the facilities that participated on this report, the State Water Board, and as well as CASA. So our project team includes Elizabeth, Sarah, myself, Chelsea Ransom, and Rob Williams from UC Davis, and the State Water Board, Charlotte, Ely, Max, and Yelena, who are all very instrumental in getting this report done. And I think it turned out to be a really great product. So I'd encourage you all to take a look at the report itself once we're done here. Definitely want to thank all of these facilities that participated in the survey and our case studies. We could not have done this work without them. And then all of our technical reviewers and advisors, including Greg, who helped review information and also helped us submit the survey or distribute the survey. So, sorry, it's a little bit finicky. All right. So the Senate Bill 1383 was really the driver for this work. And that Senate Bill 1383 focuses on several things, including an organic waste diversion component. And just really quickly, the bill was adopted in 2016, and with a goal of a 50% organics diversion from landfills January 1st of 2020. The regulations have been finalized, or they're in the process of being finalized, and they are expected to be adopted either the third or fourth quarter of this year. Then in 2022 is when the state enforcement on jurisdictions begins, followed in 2 years following then by the jurisdictions beginning their own enforcement. And then in 2025, the target is to have a 75% organics diversion from landfills, with the ultimate goal being the bold item there in 2030 of that 40% reduction of methane. Sorry, being a little finicky. All right. So California seeks to reduce the methane emissions, as we just noted, and co-digestion at treatment plants could play a major role. So just in the big picture, methane is a very powerful greenhouse gas. There's a lot of methane that's released from food waste and landfills. So reducing that food waste is going to reduce the methane. And diverting the food waste to anaerobic digestion produces renewable energy and soil nutrients. So what is co-digestion? Very big picture again. Co-digestion includes a municipal sludge component that is typically fed into our anaerobic digesters, and then an external organic waste component, which can be food, food processing waste, fog, or organics from municipal solid waste. And the bold item is really what today's talk is about. Okay, so we're focusing on the organics from municipal solid waste component. That's shown here in the bold. So that organic feedstock needs to be cleaned in some fashion, whatever it happens to be. So some level of pre-processing. And then the sludge and this organic waste are fed into the anaerobic digester. From the digestion process, we have a biogas component that is generated that we can treat and use beneficially for vehicle fuel, pipeline gas as biomethane, or through cogeneration with heat and power. The solids then are further processed through dewatering and then used beneficially off-site. And then there's a component on the side stream that requires treatment within the treatment plant. but we're not going to be focusing on that today. So there's been a lot of talk in the last few years about the excess digester capacity for that co-digestion and producing renewable energy at the treatment plants. And the state asked whether we can use this excess capacity to help meet its methane reduction goals. And the state agencies had many of the same questions about co-digestion as you probably do. How much capacity do we actually have? And how much additional capacity do we need? How much is it going to cost to implement? And how much of an impact is this actually going to make towards our goals? So based on those questions, the state water board worked with us to develop this report, which was the final product finalized in August of 2020. The report is titled Co-Digestion Capacity in California. It's a 6-chapter report with a lot of detailed appendices. And for any of you on the line that are interested in those details, I would highly recommend taking a look at those appendices. That includes a lot of the information that's in that was formed the basis of the report, but we provided all the assumptions and the details and things like that within those appendices. So the report was actually finalized in June of 2019, and then it underwent a multi-agency review at the state level, which ended at the governor's office, and then it was finally published in August of 2020. So we're going to go through the report kind of chapter by chapter, but first we wanted to put out a polling question and allow you guys to fill that polling question out.
Here it comes. Okay, should be showing up.
Okay, so if you could fill out the polling question, that should be on your screen. And the question is, what type of feedstocks are you interested in co-digesting? And check all that apply. It's multiple choice. And then if the material that you're interested in is not in this list, you can type it into the chat function. I'll give you a few seconds here.
Here we go. Almost half the audience has voted. And we'll go ahead and close the poll.
Oh, we're getting a chat that says there's no text on the screen.
We'll look into that. 108 people have voted. Here's the results.
Okay, so pretty consistent, like everything that we listed outside of maybe that sludge from municipal treatment plant. So that's great. Thank you very much for participating in that poll. And now we'll get into the major results of the chapters within the report. Starting with chapter 1, which was the food waste disposal analysis. And here, just to back up a second, there's a solid waste component called municipal solid waste. That's MSW, and you'll see that acronym throughout the presentation at points. So the municipal solid waste includes about 18% food waste, and the disposal of both the municipal solid waste as well as the food waste, as we found, follows the regional population of the state. So the most populous parts of the state, the Southern, the Central Valley, and the Bay Area, are also what generate the most municipal solid waste, as well as the food waste. So our study did look at regional differences, and we looked at the capacity as well as the food waste generation in different regions around the state. The state's population and the waste data were then used to determine the per capita food waste and the projections for the future. So we were looking out at the 2025 and 2030 timeframes, and the chart here shows in the dark blue and the dark red columns the total amount of projected food waste component of that MSW stream if there were no diversion. The shorter bars with the white on top show that if we are able to divert the food waste, what the recoverable and digestible portion of that total food waste stream could be in these two timeframes. We also looked at a high recovery and a low recovery scenario where we're able to recover either more or less food waste for the digestion component. And we did that because we wanted to avoid overestimating the greenhouse gas reduction associated with food waste co-digestion. And we looked at maintaining a consistent per capita disposal rate that's similar to what it was in kind of 2017, 2018 timeframe. But we also looked at a 10% reduction in the per capita food waste generation rate. And that was because the state has actually seen a continuous decrease in per capita generation of food waste as people, even though our population is growing, the total amount of food waste has stayed steady, which means the per capita has dropped. And so we wanted to account for that as well as the potential for some sort of recession. So for our projections, because we didn't want to overestimate the greenhouse gas reduction, we are using this 3.4 million wet tons as the 2030 value for the analysis, the subsequent analyses. So as I mentioned, we did look at a regional distribution of the food waste, and this chart or this map shows in the kind of the darkest green is the most generation of food waste to kind of the wider areas of the state where there's the least. And it follows the population growth or the population within the different areas. And so food waste comprises, again, 18% of MSW and 30% of the total organics disposal. So diverting it can play a major role in meeting the state's 1383 goals of organics diversion. So we'll move into chapter 2 now. I just wanted to check to see if Charlotte Ely was on the line yet. I still don't see her, unfortunately. She must still be having difficulty. Okay, we'll move on to chapter 2. So here we know now how much food waste we're talking about. We wanted to look at the capacity component. And here we did not look at just anaerobic digester tankage capacity because there's a lot of other things that we need to make beneficial use of the gas and process the biosolids that are generated. So we looked at the key processes that are going to be required at a treatment plant to accept the food waste with the receiving station, co-digest it in the digester, make beneficial use of the biogas. So we have to condition and then utilize the gas. Still have to have flare capacity to have safe operations. And then we've got to have processing capacity for the solids that are generated. So everything within this box is what we considered in our report. Basically what's within the fence line of a treatment plant. What we did not consider was what's outside the fence line, which is the collection and pre-processing of the food waste offsite. So the base assumption in this study was that the pre-processing would be occurring offsite and that a slurry would be produced and provided to the treatment plant for co-digestion. So we developed a comprehensive survey that was distributed to the treatment plants within the state, focusing on solids and biogas systems. And we analyzed the results that came out of that to develop our capacity analysis. So just very quickly, the survey was sent to 223 treatment plants around the country, and we got responses from 99 of those. And that represented about 80% of the state's total design flow capacity. So we thought it was a pretty good representation of the capacity within the state. We also got a good variety of the size of the plants that responded. So we took that information from the survey and we compared current and projected loads, including any organic waste that the plant is currently receiving. And then the loads that are projected out in 2030 for both the municipal, the wastewater indigenous sludge, as well as the potential organics in the future. And we compared that to the existing capacity of the systems to identify excess capacity in those key processes that I mentioned. And one thing to note here throughout this presentation, as well as within the report, is that excess capacity is reported as short wet tons per year of diverted food waste, because we wanted to illustrate the statewide impacts of organics diversion. And that is the diversion from the landfill. So that is what the terminology is. And what that means is that the food waste is diverted to a material recovery facility at about 30% total solids, but a treatment plant needs a material that is pumpable to be able to be sent into the digestion process. So we are assuming that the slurry that's produced and delivered to the treatment plant is produced and delivered at about 15% total solids. So just keep that in mind. That any of the values you're seeing on the charts is in this form, the short wet tons per year of diverted food waste at that 30% total solids value. So we looked at all of the key processes, and specific to digestion, we looked at various operating scenarios for digestion. We looked at SRT, so we looked at a 15-day SRT as a minimum, and then we considered a design SRT for treatment plants, which is usually higher than that 15-day minimum. We looked at redundancy, whether we had all of our digesters in service or if we had one of the largest digester out of service. And we considered different organic loading rates. And the organic loading rates that we considered are higher than what we typically look at for just indigenous sludge, monodigestion of indigenous sludge, which can be difficult to digest. The food waste is more easily digestible, and several plants have been able to accommodate higher volatile solid floating rates. And so we looked at the 0.2 VSLR, that's 0.2 volatile solids per cubic foot per day. Is that what's the loading rate? So we looked at that, and we know that that's achievable and maintainable at treatment plants. Some have indicated that you can achieve even higher loading rates than that. So we did consider the 0.3, and then we said, okay, if there's no volatile solids loading rate, what kind of capacity would we have? And so we looked at all of those to determine where we stood relative to the projected food waste for the capacity. And again, this is excess capacity undigestion statewide. The capacity for the specific processes at large facilities, we then extrapolated to cover those plants that did not respond to our survey. So the extrapolation only occurred for large facilities. There were 9 treatment plants that we know had digestion across the state that did not respond to the survey. So we extrapolated only for those large facilities, and we only extrapolated the processes that would scale with the influent flow. So the digestion, the dewatering, and the flare capacity, we extrapolated. We did not extrapolate capacity on anything else. And we found that we have sufficient digestion capacity for most of the projected food waste of that 2030 condition. So about 70% in our more conservative digestion operation scenario, and more than 100% capacity for that more aggressive scenario on digestion capacity. And the other thing to point out here, and this is kind of one of the major portions of the report, is that the capacity limitations are really in the receiving station, the biogas conditioning, and biogas utilization elements. Those are the key processes where we did not have sufficient capacity. And that illustrates kind of where we might be able to target investments to maximize the capacity of the digestion, which we have sufficient capacity for. We also looked at and found that we have 7 treatment plants around the state that currently have all of the system components we mentioned. We looked at the location for those facilities, and you can see that they're located in, again, those areas of the state where we're generating the most food waste, and that they're the most populous. So there's some synergy there about the location of the treatment plants and the source of the food waste. So that was good. We also found that there are limiting processes. There's capacity limitations within these 7 treatment plants where the capacity is not limited by digestion, by one of the, but by one of those other key processes. And because of that, we're limited to right now, in terms of capacity in the ground, to right now, we're limited to about 118,000 wet tons diverted food waste per year, which is only about 3.4% of that 2030 projection. However, if just those 7 treatment plants were to expand those limiting systems to match their digestion capacity, they could handle 846,000 tons per year. And that's about a quarter of that 2030 projection, just in those 7 facilities. So that helped us understand that there is some significant benefits to targeting the investments in these ancillary processes, not the digestion, but the key processes that we need for this to work out. And that leads us to chapter 3 that Elizabeth is going to summarize for us.
All right, let me just take control here. Awesome. Thank you, Rashi. So now that Rashi has walked us through how much food waste may be available for co-digestion, as well as the key processes that are required for co-digestion, I'm going to talk us through what investments would be needed to maximize co-digestion across the state. And so to do that, first we developed 2 digestion capacity scenarios. The first scenario is the more conservative scenario from a digestion standpoint. So we're matching conservative digestion operations, as Rashi mentioned earlier. So we're talking about all of the wastewater treatment plants operating at their design SRT with the largest unit out of service and at a 0.2 volatile solids loading rate. And as Rashi mentioned, that would allow wastewater treatment plants in California to process about 71% of the projected food waste available for co-digestion in 2030. The second scenario that we looked at was just matching the 2030 projection of food waste, so that 3.4 million wet tons per year of food waste. And for each of these 2 scenarios, we determined what additional infrastructure would be needed in the other key processes to fully utilize this existing digestion capacity up to each of the 2 scenarios' limits. And for each of these scenarios, we then developed planning level capital costs as well as O&M costs for these 2 scenarios, and then also for an illustrative facility to provide agencies a guidepost to more readily understand the potential costs for their particular facility. So starting with capital costs, we just looked at the capital costs needed to increase the capacity in the key processes other than digestion. We generally used a unit cost approach for the majority of these unit processes. So for biogas, conditioning and end use, as well as dewatering investments. But then there were a couple of key processes that didn't really scale with flow or load. So instead, for those processes, we used discrete costs for different sized facilities. For example, for the receiving stations, and then one discrete cost for the interconnection to a pipeline, which is not dependent on facility size. From an O&M perspective, we also looked at these costs, and specifically, we just looked at the incremental increase beyond the indigenous solids treatment. So we were just looking at the cost of treating this additional food waste that would be added to each of the treatment plants in California. We looked at labor costs, maintenance, energy, as well as additional dewatering polymer and biosolids hauling and end use costs from that food waste addition. For more details about all of these cost factors, the assumptions that went into them, take a look at Appendix 3A of the report that has a pretty good summary and also compares the costs that we were using to some other reports and other numbers, just to get a sense of where our numbers are falling. We also looked at revenue estimates, not just costs for co-digestion at wastewater treatment plants. And these revenue estimates included revenue from tipping fees from accepting that food waste, and also from biogas utilization. And specifically for biogas utilization, we looked at 3 different end uses for biogas. So first, turning biogas into electricity through cogeneration. Second, turning biogas into RNG for vehicle fuel use. And then third, turning biogas into RNG for pipeline injection. And we assumed an equal split among these 3 different end uses for biogas across the state. And we not just accounted for revenue of those commodities themselves, but we also looked at the potential revenues from different energy credits. So specifically, we looked at D5 RIN credits, low carbon fuel standard credits, as well as SGIP renewable energy credits, with the big caveat that there's a lot of inherent uncertainties in all of these revenues. So as the values change, that can really impact the economics. So specifically, for example, the low carbon fuel standard credit, which is the graph shown on the right, you can see how it's varied over time. And for the report, we had assumed $169 per metric ton of CO2 equivalent, which based on sort of the past couple of years of data seems to be still a reasonable number to be using. Similarly for, I think I went 2 slides ahead. Sorry, folks. All right. Similarly for D5 RIN prices, these have also varied over time. And the value that we used in the report was about 47 cents per RIN, which the time of the report was published was 2019, but even through 2019 and 2020, the value that we're using still seems reasonable given D5 RIN prices today. All right, so this table shows the results of the cost and revenue developed for each of the scenarios considered. And there's a couple things that I wanted to point out here. The first on the far right, the biogas use for the 3 different cases that we looked at. So for the 2 statewide scenarios, so scenario 1 and 2, again, we were assuming that equal split of biogas for electricity, vehicle fueling, and pipeline injection. And then for the illustrated facility, we just picked 1. And for that, we assumed it would be CNG vehicle fuel use. I also wanted to note that the estimated O&M costs per year are much less than the estimated revenue per year in all 3 of these scenarios. And additionally, over the 15-year project life, if you do a simple payback period, they cover the estimated capital costs. So these projects can be economically favorable. Right. Additionally, we conducted a number of sensitivity analyses for various biogas utilization options, as well as impacts on facility size and CNG and power prices. And these renewable energy, and I guess what I'm trying to say here is that the renewable energy incentives currently favor CNG and RNG and uses for biogas, but in positive economic outcomes are more likely for higher capacity facilities. However, this analysis looks at the state as a whole, but the story for each individual treatment plant may be different. So for example, if you have a facility that doesn't have a vehicle fleet, oops, I'm getting a note that my voice is fading in and out, so let me scoot a little closer to the mic here. So for example, for a facility that may not have a vehicle fleet, but has an underutilized cogen engine, electricity generation may be more favorable for that facility. So you do have to look at this on a facility by facility basis. We also looked at non-economic impacts for this report. So first, we considered community impacts near water resource recovery facilities. First of those impacts being job creation. And based on the 7 facilities that are currently co-digesting food waste, we found that job creation at these wastewater treatment plants may be limited. However, there may be additional jobs possible for offsite needs at materials recovery facilities, for example. Additionally, we looked at quantifying truck trips and noise near wastewater treatment plants and found that that would increase, but analogously, truck trips and noise near landfills would decrease because food waste is no longer being sent to those facilities and instead sent to the water resource recovery facilities. Finally, we also looked at odor control, and so all of the costs that we were assuming did include odor control to help minimize impacts of odor on the surrounding communities. In addition, we did outline regulatory considerations for water, air, and land that can affect feasibility. So first, for example, for water, if you are a facility that has nitrogen limits or TDS limits, the effluent could be impacted by co-digestion and side stream treatment, may be required depending on what that limit is and what your secondary treatment system looks like. From an air perspective, air boards are adding increasingly stringent limits on air quality, which again may impact the economics of biogas utilization. And finally, from a land perspective, for biosolids generated, you'll need to think about how to best use those biosolids, and limits on land application can necessitate longer haul distances and increased costs for biosolids management as well. So some non-economic factors to consider. Finally, we also identified potential funding sources for bioenergy and greenhouse gas reducing projects. A lot of them are shown here. For additional information, take a look at Appendix 3G for details. But I did want to mention that WEF has put out a number of fact sheets that are super useful for identifying some of these funding sources. Specifically, one of them is on public-private partnerships, which is another option in addition to grants and loans that facilities could consider. And with that, I'm going to pass it on to Sarah to talk about greenhouse gas emission reductions.
Thank you, Elizabeth. This is Greg. I just wonder if, I know Charlotte has been able to join us. Wondering if, Charlotte, you wanted to say a few words.
You know, Greg, let's keep going, and maybe I'll just say what I was going to say once everyone has given their presentations. Let's go with the flow.
Sounds great. Sorry for the interruption, and welcome, Sarah.
No problem. Thanks, Greg. All right, so getting back into the report, greenhouse gas emissions, that is a driving factor for this whole study, right, is to look at how we can accomplish methane reduction through diversion of organics and recycling that material and making beneficial use of it. So this is a really important aspect of the study to make sure that it is in fact showing greenhouse gas emissions reductions, and with respect to or relative to composting. That's since those are the two major pathways right now we're seeing in Senate Bill 1383 for diverting organic waste from landfills. So just to give you some information on how we looked at this, the greenhouse gas emission reduction factors are what we were trying to determine and develop for co-digestion. And we did follow the Air Resources Board 2017 draft methodology for compost emission reduction factors. So we considered all the same sources of emissions, which were process emissions and transport emissions, which I'll define in the next slide. And there's also emission reductions that we considered, which were the utilization of biosolids and biogas, as well as avoidance of landfill emissions. So the emission reduction factors determined by taking those emissions reductions and then subtracting the emissions to get your net factor, which is metric tons of carbon dioxide equivalents per wet ton of food waste. So in the next slide here, it's a little wordy, but wanted to make sure you had an understanding of what each of these terms consisted of. For the process emissions, it's including the pre-processing or the slurrying, the energy that took to do that, additional digester heating for that food waste component coming into the digester, as well as additional dewatering energy that's used for when that digestate or biosolids is coming out the other end for actually dewatering it. And whether we need additional polymer or not, the production for that and the transport for that to the facility. I just wanted to note that for this term in particular, it turned out that the process emissions themselves, when we calculated it, fell within and were functionally equivalent to those for landfilling. So that term in essence becomes zero because it's not differentiating from landfill. Transport emissions, similarly, we did look at transport distances and the emissions associated with those distances to transport the material to the MRF and then to the wastewater treatment facility. And those emissions were similar to composting, which were also functionally equivalent to landfilling transport emissions. And that term went to zero as well. We detail all this information in the report. So if you have any questions or want to dig deeper, it's in there as well. But just for your information, we wanted to cover that. So emissions came out that way. Emission reductions, we looked at, as I mentioned, biosolids utilization and making beneficial use of those biosolids or that product. And we looked at the associated decrease in soil erosion as well as herbicide use from biosolids application, because that is what they actually looked at and considered in that draft methodology for composting. And they had a methodology for assessing that. That said, it did not include carbon sequestration, reduced irrigation demand, or increased crop yield, and then decreased fertilizer use that we know can be a benefit or benefits of land application of biosolids. So it is noted that further research is needed for those to be able to add that benefit and that further that emission reduction associated with those benefits to this particular factor. So that's something to come. Then biogas utilization, that was, as Elizabeth has mentioned before, as well as Rashi, we looked at the renewable generation of electricity on site. And that actually, as part of this assessment, we looked at the generation of that energy going towards the additional demands that were needed as part of process support. So for the additional dewatering energy and such. As well as looking at the generation of biogas or conditioning of that into an RNG for transportation fuel. And so those two were considered and actually served as a kind of range for an emission factor. And then the avoidance of landfill emissions, we were also conservative there by looking at the decay rate of food waste in dry conditions in SoCal, or that were typical for SoCal, which is also what is looked at in the composting methodology. And so we're consistent with that. But again, we could see an even greater decay rate if it were in other conditions, let's say. So we made sure that we still were conservative so that we don't overestimate the emission reduction factor. So all that said, wanted to make sure you had those details so that if you are interested in digging deeper, that we do have that information into the report. And just wanted to give you a summary then of the actual numbers that resulted from that methodology. As I mentioned, those two emission sources were functionally equivalent to landfills, so they went to 0. So we're showing emission reductions here for biosolids use, biogas use, and avoided landfill emissions. And that range I mentioned for biogas use, 0.21 metric tons of carbon dioxide equivalent reduction per wet ton food waste is associated with renewable energy generation on site. 0.26 is associated with the low carbon fuel production. So ultimately we result in a 0.65 to 0.7 metric tons of carbon dioxide equivalent per wet ton of food waste. So, but who cares about that number unless it's relevant to something or related to something. So the next slide here that we're showing those numbers, the 0.65 for if you're doing renewable electricity, the 0.7 is the middle bar if you're going to do some renewable natural gas for transportation fuel. And then at the end there's for the composting side, we're showing relative to that, which has a 0.55 metric ton per carbon dioxide equivalent per diverted food waste or wet ton of food waste. So you can see that there's slightly greater GHG or greenhouse gas reduction potential than composting at this point in time with the numbers we have right now, even when we're being conservative. But again, reminder, we have some additional research that's already underway looking at carbon sequestration from biosolids land application, as well as some other benefits that can help enhance these reduction factors, as well as the composting reduction factor as well. So we'll see that over time. All that said, these are kind of unit factors. So what does that mean in terms of the big picture and the total amount of greenhouse gas emissions we can see reduced per year, so that we can understand what does this look like relative to the goal that we're trying to accomplish, which is 4 million metric tons of carbon dioxide equivalent reduction per year by 2030 from landfills. So as Elizabeth had mentioned before, as well as Rashi, but more recently what she described, the scenario 1, which is more conservative. We looked at that with keeping design SRTs, as well as the largest unit out of service and a 0.2 volatile solids loading rate. So being conservative, what tons can be diverted, that 2.4 million wet tons per year, and what does that result in terms of a net emissions reduction potential? And that range you see from 1.5 million to 1.7 million is what can be accomplished with scenario 1. And then scenario 2, that's more of a combination of operations that can manage or maximize the co-digestion at existing facilities. If we do those investments, we can divert 3.4 million wet tons of food waste per year, and that can get us up to 2.4 million metric tons of carbon dioxide equivalent reduction, which is about 60% of the state's goal to reduce landfill emissions. So it's very significant, very important kind of I guess, result to be thinking about and looking at and really considering, hey, if we're all going to be working together as a waste sector and wastewater, water resource recovery facility sector, we can accomplish some pretty big things by recycling this material through digestion and co-digestion. And particularly thinking about right now with all the wildfires and such, there's that added benefit that we should all be thinking about in terms of how to make use of biosolids for reclaiming that land, further reducing and sequestering carbon in that land, and further preventing wildfire in the future. So that's just to bring some of that into context of what's going on right now. But with that, I want to hand it back over to Elizabeth to start going into the small to mid-sized case studies that where we can show some results.
Awesome, thank you, Sarah. See if I can get control here. But as Sarah mentioned, so we've been talking about the sort of statewide analysis thus far, and the last 2 chapters of the report really focus on some case studies that we looked at. Chapter 5 specifically looking at co-digestion at small and mid-sized water resource recovery facilities. Oh, gonna let me, there we go. So we specifically looked at 4 different wastewater treatment plants that are currently or plan to co-digest food waste in the near future. So the first of those facilities being Central Marine Sanitation Agency, also Manteca Wastewater Quality Control Facility, as well as Delta Diablo and Silicon Valley Clean Water. And through each of these case studies, they really illustrate factors that facilitate implementation of co-digestion or pose barriers at these smaller treatment plants. But before I get into the details of those case studies, we had another poll question for you. So Alec, I'm gonna let you bring that poll question up. Awesome, so the poll question that we're asking you guys to answer is, what are the main challenges your organization faces with external feedstock processing? Again, this is multiple choice, check all that apply. And we'll see what you say in a minute here or so.
Votes are coming in. If you don't see the poll, go ahead and click on your Zoom webinar screen and it might make the poll appear.
Thanks, Alec. All right, so it looks like we've got some results in from about 87 participants. And it seems like the highest or the biggest challenge that folks are saying they're facing is the quality of the feedstock and contamination. And that, yeah, that is a big concern. So we will get into that as we go through the rest of the presentation here. There we go. All right, so the first case study that we wanted to talk through is the Central Marine Sanitation Agency. So this program, so Central Marine Sanitation Agency is located in Marin County, California, and they developed the concept of a food to energy program back in 2009 and actually started receiving FOG in 2013 and food waste in 2014. And this program is really a joint partnership with Marine Sanitary Services, who provide very clean, pre-consumer source separated commercial food waste that's processed at CMSA. And ultimately it generates biogas that's used in their existing cogeneration engine. And CMSA has found over the life of the project so far that revenues have really been higher than O&M costs. So they found it to be a good investment for them so far. And they're currently working on modifications to export excess power to the grid by adding another larger cogen engine. So the first step in this process is that Marine Sanitary Service collects, sorts, and processes the food waste into a slurry at their close by facility and trucks it to the plant. So this is really where they're trying to address some of the quality concerns of that food waste that folks were mentioning in the poll answer. To try and get the highest quality feedstock that they can to CMSA. And CMSA takes about 6 to 8 wet tons per day of slurry, about 6 days per week, and it's dumped into a below grade pit. That's mixed with the thinner fog that's also received about 5 days per week, so that it's mixed into a pumpable slurry. They still do send it through a paddle finisher to polish it to get out some of those final contaminants. And that blend at about 7% solids is then fed to the digester to produce biogas. All right, so now I'm going to talk through some of the factors facilitating co-digestion at CMSA. And really the initial driver for this project were the California regulations to reduce greenhouse gas emissions, as well as a grant that was received by PG&E to do an initial co-digestion study with Marine Sanitary Service and the city of San Rafael. And through the results of that study, they took those results to their board and also to the city council. And the board and council were very interested in exploring co-digestion further. So really getting the board on board is helpful for moving these projects forward. From there, they then solidified agreements with Marine Sanitary Service to accept food waste, as well as with Marine Clean Energy for purchasing the electricity that would be produced. And finally, Marine Sanitary Service also did a lot of community outreach for the project to ensure that they were getting a quality feedstock and folks knew what could go in the food waste bin and what couldn't to minimize contamination. And CMSA also ran the numbers to make sure that the project was going to be economically favorable. In addition to that, there were also a number of factors that were impeding co-digestion at CMSA. Ultimately, they were able to overcome all of these, but I did want to walk through some of the concerns that they found. The first of which being power forecasting. So California ISO requires registration and power forecasting for any generation over 1 megawatt. And CMSA found that fluctuations in digester gas production posed a risk to accurate forecasting and would result in fines that would decrease the benefit of the project. So to get around this, CMSA decided to pursue an engine that would not exceed 1 megawatt to avoid the need for power forecasting. Additionally, CMSA was an early adopter, so they were able to lock in a very favorable electricity rate with Marine Clean Energy. If they were to renegotiate or if another agency was looking at doing something similar, Marine Clean Energy agreement rates to sell power to the grid would likely be lower, again, affecting the economics of the project. Finally, PG&E and Marine Clean Energy requires certain interconnect interlocks to be able to export power. And while this is not insurmountable, it did add cost to the project and something to think about if you're an agency considering this, doing something similar. All right. Also wanted to share a few lessons that CMSA learned and some advice that they had for successful operations, specifically at their plant. First of which having to do with O&M. So they are, it's very important to them to get high quality feedstock, as again, a lot of you mentioned on the poll. But even with that high quality feedstock, they still need a paddle finisher for polishing. And they've also found that maintenance has cost more than originally expected. Again, still revenue positive for them, but something that should be thought about if you're thinking about a project like this at your facility. CMSA also conducted a risk analysis to figure out which critical spare parts they needed to keep on hand or on the shelf at their suppliers to make sure that the fog and food waste receiving station stayed up and running as much as possible to minimize downtime. And they also had some issues with coatings, so they wanted to note that coatings can fail, something to think about during the design of a similar facility. CMSA also had some process impacts that are worth noting. The first of which is that they try and avoid biogas flaring and digester upsets by maintaining digester feed and storing gas. They also have found that they need to increase the amount of polymer used to maintain the same cake dryness after adding fog and food waste. And finally, their last tip is to assign a versatile organic waste coordinator and champion to make sure the project runs smoothly and that there's someone who's looking over the project sort of from a holistic perspective, making sure things are moving forward. Right, so the next case study that I wanted to talk through is Delta Diablo. So Delta Diablo is located in Contra Costa County, and they, at the time of the report was finalized, they were in the planning phase of the project. The plant currently receives about 10,000 gallons per day of fog for co-digestion, and they're looking to add food waste to that mix through a public-private partnership with Mount Diablo Resource Recovery Facility. And so Delta Diablo and MDRR joined together and created the East County Bioenergy Project, which was planned at the time of the report to take 285 wet tons per day of food waste at 12% solids, about 5 days per week. And right now, Delta Diablo has cogen that's producing about 0.8 megawatts. And with the project, they could see that increasing to 2.5 megawatts if they wanted to expand their cogen. All right, so this East County Bioenergy Project includes a comprehensive plan for modifications at both the Mount Diablo Resource Recovery Facility as well as at Delta Diablo Wastewater Treatment Plant. So at Mount Diablo Resource Recovery Facility, that's where they do all of the pre-processing and polishing to produce an organic slurry from municipal solid waste. That organic slurry is then trucked to Delta Diablo, which is located nearby. And Delta Diablo then co-digests that, and there's a number of project elements at the wastewater treatment plant site to make sure the plant is able to process all of that food waste. Delta Diablo also hired an owner's advisor and specialty legal assistance to help with the project development. And now getting into some factors facilitating co-digestion at Delta Diablo. The project was originally actually started by Mount Diablo Resource Recovery Facility because of the organic diversion regulatory drivers, so AB 1826 and SB 1383. And they found that Delta Diablo shared a lot of the same goals as MDRR. And Delta Diablo specifically was interested in increasing their renewable energy and utilizing excess capacity at their plant. So because of that, the two facilities partnered together to join the to create the East County Bioenergy Project with a memorandum of agreement that included a 50-50 cost share for all the planning studies that they then conducted. So once they formed that partnership, they did a lot of planning and alternatives analysis to look at a number of different projects to figure out what project made the most sense for the two facilities. And then Delta Diablo hired an owner's advisor to look at future revenue potential and conduct financial modeling and assess the best biogas end use for them. There are also some factors that are impeding co-digestion at Delta Diablo, the first of which being inadequate funding. So they're applying for several grants and loans to help make the project more economically viable. Delta Diablo was also very interested in risk, and they created a risk register for a number of different types of risks that they saw, and were interested in how to assign those risks to Mount Diablo Resource Recovery Facility versus Delta Diablo as the project moved forward. And finally, the final factor impeding co-digestion in Delta Diablo is really third-party coordination and making sure that all of the regulatory requirements for air permits, solid waste permits, as well as interconnection agreements and power purchase agreements all came to fruition at the same time and were all coordinated across one another. And so with that, I think I will pass it off to Sarah to talk about the other two facilities.
Awesome. I'm gonna get some control here. All right. So next one is Manteca Wastewater Quality Control Facility. There we go. Which is located in Manteca in San Joaquin County. And it was a waste to fuel program that was kind of pushing this along. And they had 5 projects underway at the same time to be completed as part of this whole effort. And they're listed there in the bullets where they had new digesters and improvements to their digester control building as well as existing digesters. And then a food waste and fog receiving facility or facilities, and then compressed biogas fueling facilities that they were looking to implement, as well as a food waste separation project. And that with all of that put together, they would be available to accept 3,400 wet tons of food waste slurry per year. Some of the facilitating factors or the pushes that were driving them to do this project or these projects in Manteca really were the regulatory drivers of looking at the organics diversion via the different legislation items there that you have listed. And then proximity to the CNG fueling station. There were 4 old trucks that needed replacement, but they had some a nearby fueling station, and they had partnerships that naturally led to some discussions of how they could put all of this together, being that the city was managing the wastewater treatment plant and solid waste management out there, that there was this natural kind of synergy and discussion that they could have and ability to make decisions more quickly than otherwise, as well as the county owned and operated the material recovery facility. So they would come together and have these discussions about how to implement these facilities and make this project come to fruition. But another very key and important element was financing. And they did have city funds and bonds, but a CEC grant as well as a air quality or management district grant through the San Joaquin Valley Air Pollution Control District that really helped push these projects going forward, or were helping to push them going forward. Some impeding factors for the projects, though, there was still inadequate funding for equipment procurement, particularly for the food waste separator, and the revenue potential that originally in the plan that was put into place, they looked at the higher value D3 RIN versus the D5, where the value for co-digesting biogas is at this point in time. And so that was a bit of an issue. And then other regulatory hurdles were in their way, be it they have land application restrictions in the area, and the consideration of the increased nitrogen load from the food waste coming in to their water stream, and thinking about the limits that they have on their discharge to the San Joaquin River when they do discharge there were some impeding factors. So with that, I'll go into the next one, Silicon Valley Clean Water, where they're located in Redwood City in San Mateo County. And they had a pilot program, which they were looking at food waste co-digestion pilot for 3 months. It ended up being 3 months. They accepted 3 to 6 wet tons per day of slurry from organics extrusion press, or an OREX, of black bin waste, so that they could pilot that and see how that goes. And with the results that they found, they just, at that time that we did this study, they were intending to proceed with the full-scale implementation. And actually there was a plan to have an extrusion press nearby in a partnering solid waste management facility. So to do this pilot, they actually did have to modify their existing fog receiving system so that they needed to repurpose one of their 2 subgrade fog tanks to receive that food waste, add in dilution water and mixing capabilities, as well as a feed pump for the slurry itself. They did find that there was a significant amount of contamination, 15 to 20% contamination, so they needed a paddle finisher to reduce that. And they also needed additional storage tank for clean slurry, and then bins to capture all that contamination. But they did have an existing pump to feed the slurry to the digester in the end as well. So there's a bit of work to get this in place. But some facilitating or kind of driving factors for running this pilot, they had both an energy master plan and energy recovery plan that really, the recommendations that came out of those were to run a pilot and see how the results would look and see if it was worth going to full scale. They had nearby supporting partnership with South Bayside Waste Management Authority, and used that relationship and had shared objectives with them to go forward with this co-digestion, to work together to have this organics extrusion process moved to the SBWMA so that they could successfully run this pilot and go forward and with a full scale if possible. Financing was also available. They had a CalRecycle grant for the equipment procurement, as well as a CEC grant for the technology demonstration. So these factors really helped push this forward. There were some impeding factors that they managed through from a regulatory perspective. The air permitting for this pilot project was a little bit more cumbersome than anticipated, and it took 2 years to resolve, which threatened funding, but they ended up getting it resolved with the Air Quality Management District in the Bay Area. They also had solid waste permit or potential permit due to the black bin nature of that waste, but they could be granted an exclusion for that particular permit. The other side of things is contamination. We mentioned that 15 to 20% contamination in the extruded food waste received. It's pretty high, pretty time consuming to deal with, as well as they needed that additional polishing step and to work through those little issues that they had. But they had some lessons learned they wanted to share, is that one, securing agreement early with the nearby or partnering waste management firm is very important and worked well for them. High quality feedstock, getting back to that poll, yes, high quality feedstock is important, less contamination. It's essential for reliable operations in general. The screen type on the paddle finisher turned out to be important as well, the selection of that for reliable performance, as well as having enough bins to capture the contaminants that were coming off of that waste. Delivery vehicles, interesting, vary in size. So that's something that was just maybe more unexpected, and you need to plan accordingly for how you're going to be receiving that material. And then preliminary results at the time of the study did show more biogas production and easier dewatering. And so they were wanting to have their full results in order to make decisions about going full scale going forward. But this is what we captured at the time of this particular study, which we finished in June 2019. So in summary of all of these small to mid-sized facilities and case studies, there's some common factors that really drove the facilitation of the decision to go forward with co-digestion or consideration of co-digestion. And state laws and regulations are driving that, as we're seeing with Senate Bill 1383. Supportive partnerships that they have developed or did develop out of wanting to do these with waste management firms and utility providers. Community support and their board support, super important in driving. Planning and feasibility studies, really showing that this could be something that's feasible for folks to consider and something worth investing your time in. Financing and assistance through loans and grants, very important. This is outside of our toolbox in terms of we are, as wastewater agencies or water resource recovery facilities, our objective is water quality. And so this is a bit outside of that main objective. So for ratepayers, we want to try and protect them as much as possible from increases from that. So if we can get grants and other alternative funding, that's a driving factor. And then revenue from offsets through tipping fees and biogas utilization. If they saw that that was a potential, that was also a driving factor. But common barriers to impeding these types of projects were also regulatory in nature. Whether it was related to effluent quality from receiving a higher nutrient load and considerations there, and sorting through that, air quality, also looking at what you do with your products in terms of land application if it's available. Insufficient planning and feasibility could lead to being an impeding factor if you didn't have enough in place or understanding of the integration of these systems into your facilities. Inadequate funding definitely led to some issues and barriers for folks. Feedstock contamination and competition for organics was mentioned as well in the diversion through composting and other impacts on tipping fees. So these are some common barriers that were gleaned from the case studies for small to mid. I'm going to hand it over to Rashi to get into the larger facilities that have been doing this for a while and what we found from there.
Okay, great. So we're almost done here. So bear with us and then we'll get to Q&A. So we looked at not only the small and medium-sized facilities, but also larger treatment plants that have been doing co-digestion for a while. And the first, so these case studies were to illustrate the specific benefits and challenges associated with co-digestion. And here we looked at the East Bay Mud main plant, which is 120 MGD, 80 WF facility, and the joint plant operated by LA County SAN, which is has a 400 MGD design capacity. So first, East Bay Mud. This is a very well-known plant, and their resource recovery program, or the R2 program, leverages the existing excess capacity for organics loads in the area. This plant operates their digesters. They have 11 digesters. They operate them thermophilically. They've got several cogeneration options with engines and a gas turbine. They are net energy positive on average. They are selling power back to the port, the local power consumer. And their R2 program includes a variety of organic feedstock. So this is really important. The work that we did and what we found from this facility is not specific only to food waste slurry. It includes everything that is fed into their digesters. It includes a lot of other things beyond the food waste slurry, and that slurry actually only comprises a small portion of their overall feed. So they have produced through this program tipping fee revenue and energy that exceeds the added costs for biosolids and other operating expenses. So you can see in these graphs that they have generated a considerable amount more in the biogas. So this is pre-R2 and this is post-R2. And they've also generated more biosolids. But again, with the 100 to 150 trucks per day that they're getting of their feedstock, they have generated significant revenue, including $1 million a year in tipping fees, $2 million in power offsets, and another $1 million in power sales. And that has offset the $1 million per year increase in biosolids costs at the facility. They continue to address the challenges that are posed by the R2 program. They are concerned about the impacts on nitrogen and potential nitrogen removal requirements that will be imposed on them as well as other agencies in the Bay Area. The TDS content and the impact on the effluent because they use their recycled water for cooling water purposes. So the TDS or the salinity can impact the use of that recycled water. And they currently have co-digestion and the variability in the biogas production really impacts that utilization equipment. So they have worked through different ways of trying to level out the variability in that biogas production. And they are now considering incentivizing deliveries on the weekends to help even things out across all 7 days of the week. The value of their wholesale electricity is decreasing. And so that's shifting the economics of their biogas utilization options. So they were considering pipeline injection. They were impacted by some Cal OSHA regulations relative to that, but I believe that recent communications with Cal OSHA have improved this. And so this may be back on the table potentially for consideration. And one of the biggest things that they've had to deal with is the grit and the abrasion of the material that they receive in the fog and food waste specifically, and the increase in O&M associated with that. So they are, I think they have conducted a test for grit removal from a 6% TS slurry that I believe they're actually going to be presenting on at WEFTEC. So moving on to the LA County Sanitation District's joint plant. This facility conducted a long-term demonstration of specifically what we're talking about, this food waste slurry that is produced and processed offsite and brought into the plant as a slurry. They have 24 digesters available. They operate mesophilically, and they have several different options for biogas utilization at the plant as well. The demonstration, the full-scale demonstration plant was preceded by numerous feasibility studies and bench scale testing conducted in the research labs of the county or the districts. They partnered with Waste Management for acceptance of the source separated commercial organics, and Waste Management produced the bioslurry that was produced offsite and trucked in. And this demonstration ran for quite a while. And the demonstration proved successful at LA County San, and they have now built a full-scale pre-processing facility at their own MRF at one of their landfills, because the LA County Sanitation Districts covers both solid waste as well as wastewater in LA County. And so you can see here in the data, they definitely saw this increase in biogas production. They tested the demonstration with 4 digesters, 2 of which they kept as control, and the other 2 that they swapped between being test and control. And so these are the control digesters and these are the test digesters. So they saw the increase in the biogas production, they saw the increase in biosolids production. But even with the impact on the biosolids, they felt it was worthwhile to move forward with a full-scale facility for the pre-processing. They've also got a vehicle fueling system project that's underway, and they will construct a larger slurry receiving station at the joint plant in the future. In terms of the challenges, they were similar to what East Bay Mud found with the grit and the glass and the associated O&M. So they're also considering ways of improving the removal of those components within the slurry. So before we close, we had our last polling question for you. So if Alec could bring that up, that would be great. Having talked about co-digestion for over an hour, just wanted to find out what your agency is planning on doing. If you're currently co-digesting, if you're not co-digesting, if you're considering it, if you don't know, or if it's just not applicable. If you could fill that out, give you a few seconds here.
Yep, we got 70 votes. If you don't see the poll, try clicking on your Zoom webinar window and the poll window should appear. 90 votes, almost there.
Alec, your team's chat might be popping up on the screen. Okay, so we're either currently co-digesting, we're considering co-digesting, or it's not applicable. So thank you for that. And with that, we are going to have our very last slide. So what's the takeaway? If I can get to the slide. Okay. So co-digesting food waste slurry at treatment plants can help achieve California's mandates and goals if the challenges we notice, and there are many, and the investment needs that we identified are addressed. The feasibility of co-digestion and gas utilization is absolutely at a facility level. So we provided information at a statewide level, but we have to look at things case by case for what makes sense for specific facilities. And in Appendix 5D of the report, we provided a kind of a decision support tool. It's basically kind of a flow chart of questions that a facility can ask to help them understand whether co-digestion is going to make sense at their facility or not. So we would, if you're interested in it or if you're considering it, we would suggest that you take a look at that support tool to help you in that process.
Thank you so much, Rashi, Elizabeth, and Sarah. Tremendous presentation, a lot of information to go over here. And we do have a number of questions that I can just start posing. First one is for the short wet tons of food waste assumption, what was it assumed in terms of the water needed to be added to dilute in order for the wastewater plant to receive it?
Right. So while Elizabeth and Sarah were talking, I did provide some responses to a few of these questions as we were going. So for that one, we did assume that the dilution was going to be occurring upstream of the treatment plant, so that it would be produced and provided to the treatment plant in that at that 15% total solids consistency.
Thank you. And with the lower carbon intensity values that have been derived for non-wastewater treatment plant biogas, is there a concern for saturation of the market for non-POTWs, and how might that risk be mitigated?
Right, Sarah, do you want to take that one?
Yeah, I think I need to hear that again one more time, because that's a good question.
Well, it was the fact that carbon intensities for dairy digesters, for instance, are far lower than wastewater plant digesters. Yep. And so does that create a concern for saturation of the market from non-POTWs? And is there a way to mitigate that risk?
That is a good question. I know that It's from a saturation point, I don't think so. I know that we're seeing some more dairies and some more, I guess, projects in that sense, but there's a lot more encouragement from the POTW perspective to develop these partnerships and develop your site-specific carbon intensity. That may not be the default factor right now is a bit high, but you have this ability to have a project-specific carbon intensity that can get you to a lot lower. Not as low as dairies most of the time, because we can't go back to saying, oh, well, if it was going to a landfill, we could say that we, for the sludge itself. But for food waste, we can do that, and it can actually provide for a pretty significant or low carbon intensity factor for these particular projects. So I think we're seeing support from the State Water Board as well as Air Resources Board through their low carbon fuel standard to by this pathway that we can have a site-specific CI that we won't see, or that will help mitigate some of that risk a little bit more, if that makes sense.
Yeah, it does. Thank you. And that was a difficult question. And I would just add that the Air Board has definitely been engaged and wants the wastewater sector to be involved in the LCFS program. And they are working with us to give us the value of diverting the food waste from landfills and working that into the CI.
Yeah.
Then just a follow-up one that is related is, was there a particular CI that was assumed for wastewater plants for the LCFS credits?
Oh yeah, Elizabeth,
Yeah,
particular number.
there was. We assumed 45 grams of CO2 per megajoule, and that's the biomethane CNG value.
And that's their default value, I guess,
Yeah.
right?
Yeah, to be
Correct.
conservative.
Right. Then there was a question of how will the increase in biosolids production be managed? What level of increased production volume was assumed? And then they had an add-on of will alternative daily cover as a use still be viable?
I don't think I heard the second part of what you said. You went out a little bit, but was that considering what the increase in biosolids from the additional food waste would be and how that might be a risk because of these end uses being at risk?
That's right.
Okay. So I guess, and this is something you could actually weigh in on too, Greg, from the Senate Bill 1383 perspective, anything that you would take as far as a diverted food waste and you're cycling it through anaerobic digestion, they're trying to create procurements. And one is they have a required procurement for compost. We're trying to see that gets expanded to biosolids. But they also want to see this material used locally. And so that there is some language in Senate Bill 1383 that hopefully gets adopted soon that would help push back on some of these local ordinances, county ordinances that are limiting land application of Class B material or other, depending on what the ordinance says. But this is where I'd probably hand it to you, Greg, to give more detail there.
Yeah, thanks. And it's, you're right. The regulations do include language that will prohibit those restrictive ordinances that do limit land application. And while ADC won't strictly be prohibited, it certainly is going to be discouraged and will no longer count as a beneficial use under AB 939 either. And as jurisdictions and the state need to comply with the mandates, biosolids will likely be considered the cleanest organic waste there is, and therefore the lowest hanging fruit. So we don't expect that ADC will continue as a viable option for too long.
Right. So then it underscores the need for that land application or ability to do land application, or then it may require further treatment like for composting to bring it to a Class A so that it can be land applied somewhere nearby.
Right. And another one is a question as to why would polymer use increase for dewatering through co-digestion? And then a secondary part of that was there an increase in chemical use needed for hydrogen sulfide control?
Okay, so in terms of the dewatering, what we found for dewatering processes is that depending on the type of organic waste that is digested and then dewatered, it can either improve dewatering or it can reduce dewaterability and increase polymer demand. It's really a matter of the characteristics that are introduced into the system. So dewaterability is impacted by multivalent cations, by EPS or exopolymeric substances, by primary to secondary sludge content, and kind of just the overall water content of the material that is introduced. So a lot of those things go into it. And so I think we noted that Silicon Valley found in their preliminary results that they had an improvement in dewaterability. And then CMSA found that they had to add more polymer to maintain the dewatered cake dryness that they were getting. So it really does depend on the material that is received on site and the impacts on the chemical characteristics. On the H2S content, we did account for odor control in our capital costs. Odor control is very important. The stuff does smell and you do not want to smell it. Your neighbors don't want to smell it. So we definitely did include capital cost for the odor control. I don't remember in terms of the actual chemical consumption of H2S if we assumed a chemical scrubber specifically. And we'd have to get back to you on that particular part of it.
Okay, well, thank you. And I see we are at about our bewitching time. I didn't know if Charlotte, you wanted to have any concluding words?
And Greg, I think Alec also said that he's available to keep this going in case people want to stay on. But yeah, absolutely. Charlotte, you want to?
Sure. I mean, I'll just say it's a pleasure to conclude the day's webinar. I'm looking out my window right now and I'm seeing that the sun is yellow rather than red for the first time in what feels like weeks. And I think this, extreme heat and fire really magnifies the need to invest in co-digestion and renewable clean energy projects. So just a thank you to CASA and CWEA for hosting today's webinar and the Carollo team for your excellent work on the presentations today and the report. I think in conclusion, as far as I am concerned, as far as the climate and conservation team is concerned at the State Water Resources Control Board, co-digestion is worth the work. Realizing our co-digestion potential here in California, it's not only going to require investing in infrastructure, but also navigating these complex regulatory, technical, and institutional challenges. But despite these challenges, we're seeing that co-digestion will benefit medium and large wastewater treatment plants. As far as the, water board, is concerned, and US EPA, where I used to work, sort of advancing co-digestion for some time. Co-digestion, it boosts bioproduction, which when used on site significantly reduces a wastewater treatment plant's energy costs. And the less a facility spends on energy, the more it can invest in improvements that protect water quality while moderating rate increases. And to the question about the SRF, to the extent that a facility, an agency applying for that funding can demonstrate that their projects will protect water quality, it is a competitive application and you guys should move forward with it. So I'll just close by saying here at the State Water Board, we really look forward to working with our industry project partners to get more of these projects off the ground. So thank you again to the team here and to all the attendees today.
Thank you, Charlotte, and I second that. Thank you very much, Rashi and Elizabeth and Sarah. Great jobs. And just so you are aware, the report is available at the CWA website at the link shown here. It's also available on the CASA website. And this session, and even in more detail, I believe, will be repeated during the annual conference virtual session coming up on October 21st. Sarah will moderate that session, just so everyone is aware of that. And thank you again very much, everyone.
So Greg, do you want to, we can keep going on the Q&A unless,
Yeah, I've got a few more questions.
yeah, I think we can keep going if,
Okay, if
for a few
people,
more minutes, I think. I don't want to take up everyone's day.
sure. So here was one. What % of available food waste can be considered high quality?
It's a trick question.
Yeah.
I don't think
Depends on-
any of it can be considered high quality unless it's pre-processed and screened offsite to remove the contaminants. So it's very important that the waste management sector be equal partners in this with the treatment plant folks, because they're going to help us get slurries that are as high quality as possible. But even when we get those high quality feedstocks, as noted by CMSA in Silicon Valley, we may still need some, finishing at the treatment plant itself. So there's a little bit of debris that still remains in there. But it's very important to have that pre-processing offsite to create a consistent and high quality feedstock.
I think that's an excellent point to bring up. Is we see a real opportunity and need for collaborative partnerships with the solid waste sector, because it definitely is a two-way street, needing the cleanliness of the feedstock and they needing a shore repository to take the waste. Here's one. Is there a conversion efficiency factor applied to converting that food waste into a clean slurry? I don't know if that was something that was considered.
Sorry, can you repeat that, Greg?
Yeah, the question was whether there was a conversion efficiency factor somehow applied to transferring the food waste from a waste into a clean slurry. I'm not sure where that factor would be applied.
We did, so when we were looking at the food waste, so we had the overall food waste that's produced in the state, and then we had assumptions built in relative to that on how much could be divertible and digestible. And we accounted for a 50% recovery factor of the food waste to provide that digestible and recoverable portion of the food waste that would be provided as a slurry to the treatment plants. So that might be I hope that's the answer to the question, if we understood it correctly.
Great. And do the greenhouse gas reduction factors consider the avoided use of gasoline? I guess,
Diesel.
yeah, probably.
Yeah.
So, go ahead. Sarah.
Yeah, that's embedded in the when we're looking at transportation fuel and generating the low carbon transportation fuel, that emission reduction factor has included in it the displacement of that diesel.
Okay. And here's a perhaps difficult question that I would just insert for myself to get your takes on it. In the proposed regulations that are about to be adopted, you mentioned the procurement requirements, Sarah. One of those is for beneficial uses of biogas, that every jurisdiction that diverts organic waste has to buy back some product or procure some product that results from that diversion. And you're right that right now the eligible products include compost and then beneficial uses of biogas. However, they stipulate that we need to subtract out the biogas that is produced from our sludge digestion and only count the biogas produced from the diverted food waste. How significant of an impact do you think that might have on the viability of co-digestion projects? And I'm sorry if that's a trick question.
No, I think that's a great question. And that's something that in the analysis of looking at the feasibility that Elizabeth, you summarized in the slides, that we only considered the biogas generated from the food waste that was diverted as part of that feasibility. And it did show as, in the end, as, you know, something that's viable. Also looking at the credit values and such that were in place at the time, but as also Elizabeth showed that those have stayed consistent in terms of what we considered a year ago when we finished this versus now, and how that those values have changed. But Elizabeth, did you want to add anything to that?
Sorry, I was muted there. No, I think you did a good job of answering that question, Sarah.
Yeah, so
That's good to know. Then you still found it was a viable project. That's very helpful.
Yeah.
Let's see.
Greg, I think there's a number of questions about the nitrogen load that I think we need to address. Definitely, we noted that in the regulatory drivers and the things that are going to potentially impact co-digestion on a facility by facility basis is that nitrogen limit, whatever that emission, that effluent limit is now, and if there's more stringent limits coming in the future, the nitrogen portion of that return stream coming back to the secondary process definitely has to be considered, because it may end up requiring some sort of side stream treatment or trigger something else. So that's definitely a huge part of the equation that has to be considered at a facility by facility level. The study specifically looked just at the solid stream, so we did not ask facilities about their liquid treatment capacity systems. That was quite a bit beyond the scope of our study.
Okay. Yeah, that's an excellent point. Well, that looks like it is the majority of the questions that I had written down. So I think that we can probably conclude. Although it looks like we still had a good number of participants still on, so that's great.
Good time. Dedicated professionals. Great job, everybody. Thank you so much for joining us.
thank you. And thanks to everybody out there still.
Thanks very much. Really appreciate it.
Thank you. And if you still have questions, all of us are perfectly willing. Our emails were kind of snapped on that screen quickly, but any of us would be happy to talk to you further about any questions you might have. And the report is available in a number of locations. So it is publicly available. Please feel free to review that. Thank you so much for your attendance. We really appreciate it.
Well, thank you very much. Thanks, everyone.